pull-up device? Yeah. Okay. The depletion. Okay. As I said, you have to choose the value of that resistance so that it physically works. For the discussion today, I don't know. Dick may get it a little bit in ratios this afternoon. Part of making the value of that resistance right is to adjust the length and width of the device. As far as functionally drawing the thing or designing circuits before you lay it out, you don't worry about the physical size of it.
No, I was asking more when you're using one color pen as you are there.
Oh yes, I'm sorry. I missed what your point. Ed indicated that in the book, because yellow is not always available, you sometimes put a wider part right there, a thicker line right there, to indicate that it's a depletion mode transistor. And that's absolutely right. I will sometimes leave that out because whenever you see a device such as this with a gate connected to the source, it's almost certainly a depletion mode transistor. that doesn't make it. You can make it a depletion mode transistor. You can certainly take an enhancement mode device and connect it up that way, but it's just in normal circuit conventions, it just isn't very useful because it sits there and stays off all the time.
Don't they do something physically, Doug, to it, like ion station? They do something else.
Yeah, we're gonna get to why that's why it's called the yellow transistor. Is you make it different by putting some yellow stuff on it, but with a brown pencil. But yes, in the book, this circuit configuration or convention is used to explicitly represent a depletion mode transistor. Okay, now one of the things which I said earlier was that we actually like to include thinking about the layout process in the initial design. We actually want to be thinking about how this circuit is going to be laid out as we go about the design process. And so these circuit diagrams don't really tell us what we need to know as far as how this thing would lay out, because they're just very schematic representations and they don't really describe the layout structure. And so that's what I want to talk about now, is a representation which will allow us to draw these things more easily into something that can be fabricated. And for that, we use a representation called stick diagramming, which is something you've seen in the book, and if you've done the reading ahead of time. And it makes use of multicolors. And the reason we use all these different colors in this process is because in the fabrication process, there are really 3 levels of interconnect which are available to us. And they're not only interconnect, but they are actually 3 levels which, when manipulated in the right way, not only create lines connecting devices, but they also create the devices themselves. And we call those 3 levels by the basic process name, and we use the following colors to represent them. We have the diffusion level, and this is used for defining gate source or drain source regions and for some interconnect. We have the polysilicon level, and we use red for that, and that's used for interconnect as well as defining the gates of transistors. And we have the metal level, which is blue, to describe metal interconnects. Now you can, for the next couple of days, you consider the technology to be a 3-level PC board process that have these 3 different layers associated with it, and the layers have the following properties. Number 1, you can run metal anywhere, as far as crossing over other lines, and they won't have any effect. However, so the metal can cross the green or the red with no effect on the circuit. However, if you should take the red and cross it with the green, you get a transistor. Yeah, purple, whatever. Okay, how does this transistor relate to to the diagrams that we've been doing over here. Okay. Okay, let me just draw another representation. This is going to be the stick representation for these various circuits. Number one, we had a simple transistor up here, and the drain and the source regions, as I said before, were defined by the green level, and you actually made the transistor, you formed the transistor by crossing it with this other layer, which is the poly. So this is the gate, and this is the source. All right, that's really doesn't matter. Drain, source. As far as you think, well, what's the difference between a drain and the source? When you actually get down and see the fabrication process, there's absolutely no difference at all between the drain and the source. And we normally assign the name drain to the more positive node and the name source to the more negative node. But as far as fabricating the transistor, it looks the same from both sides. And in fact, it's very nice because it's bidirectional device, and you can use it. Signals can go through it in either direction, depending on as long as the overall circuit is okay. Okay, and now over here, remembering that we've replaced all our pull-up resistors with depletion mode transistors. I won't tell you how to make resistors yet. They just take up a lot of area, which is why people don't use them. Okay, so you have a transistor up here, which is the depletion mode one. And then you go down further, and you have another transistor down here, which is the enhancement mode one. And then we see that this guy is connected to the source right there. And this, of course, is the same guy down here. So now they're the... As you can see, stick diagrams, other than changing pencil hands, is a lot faster than making all those squiggly lines associated with circuit diagrams. And they also actually convey more information, even though they're easier to draw, because they really describe how the layers cross each other, how they interact, and so forth. These stick diagrams are really just slightly higher level than layouts, and you can largely do a mechanical transformation from stick diagrams to layouts. And in fact, we'd love to make that a mechanical translation. It's one of the tasks for somebody in the audience, I hope. Okay, so these are the various things. We started with a circuit diagram or some simple models which you're familiar with. They have a logic representation. They have a stick diagram representation. And depending on what particular kind of thing that you're interested in talking about at any particular time, one representation or the other may be more appropriate at that time. Is this clear? Is that the stick diagram and the transformation between it and the other things? People basically understand that, and you can cascade these things and get AND gates of 4 in a row and 10 in a row, and you'll find out why 10 in a row is not such a good idea later. But for tonight, consider that okay. And it really sort of harks back to the days of relay logic, where you just had relays in series and in parallel performing various interesting functions. And in fact, a lot of the interesting structures which you can build with nMOS transistors can be found back in the 1950s books on relay logic. So if you want a little history, you can go back and see how applicable that ancient technology is to the nMOS transistor logic layout design of today. I'm going to stop. We're going to take a break now for about 15 minutes, and then Dick will take the last half of the class and tell you about some much more interesting structures other than ANDs and NOR gates.
Doug, it's been suggested that I stand up here in the light and that you put slides up for me. Is that okay? They're all in order here. Just go through this stack in order until you get to the homework. That's the last one.
I don't want to be in that one. Okay.
Are we ready? Okay, I'll take off where Doug left off. Start talking a little bit more about the notations of circuits, stick diagrams for out. Of a NAND gate. Expect lines with some sometimes wider, sometimes the same. The diagram which Doug showed is on the right. Small here. It contains a load device and two devices in series. Show us the bottom part of that. If you push it up a little bit.
Wait a second. Under the
indicate that the green region the red. A green line crossing a red line. This is to indicate that the red is actually on. Is in some sense underneath. You'll find us later, and you'll find out what it means to be underneath. The diffusion that Doug mentioned actually gets put on after the red, and so there's no diffusion underneath, and that's why there's a transistor.
I see there's a line but no diffusion.
There's a line. You draw it, but it doesn't actually get diffused. It makes a transistor instead.
Okay.
Okay. This funny structure here is the contact that connects this output node to this pull-up device, which is a long, skinny one. And it's drawn with a box around it, which may be indicated in yellow if we have yellow available, or any kind of a box to indicate that that's a load device or a depletion mode transistor. Okay, let's look at the circuit diagram and the logic Doug already showed you. This is all for the same thing, the NAND gate. The circuit diagram has with a gate devices, either that way or with the heavy line as in this case. On the right is the familiar NAND gate logic symbol, and then on the bottom is an important example because this is the introduction to mixed notation. We mix notations a lot. In the case of whatever the relevant information. In this case, the NAND gate is shown in its stick form on the bottom with a transistor circuit form as the load, connecting through this transistor into a logic element, which is an inverter. So we'll see more various kinds of mixtures of notation later. Keep in mind that it's all the same stuff, and if you ever see a diagram with different notations in it that you don't understand, please ask and we'll try and clarify it, make it more uniform. This is more a convenience. Things like the inverter, where all we want to indicate is that there's an inverter function there, not how it's made. Doug mentioned the models for the transistor devices as a relatively technology independent model. Two models which we will use. They're a switch or a load. The elements will be made out of these two types. For switches to ground, NAND gate has them in series. And this brings us to another type of logic that's easy to make in the nMOS technology, and that is using switches not for making gates. This is typical of the kinds of things which is the old books on relay logic are circuits made of this kind. And so on. So, for example, input 1 or input 0, depending on the state of the select. This is logic on here, which turns that switch off, and thereby. Notice also that it's bilateral. That an output, except. That is, gates made out of switches and loads. Between the two of these, oh, I see the eraser doesn't work very well. A device model we need, which is not quite technology independent, but depends on the fact that this is a field effect transistor technology, is a capacitor. You don't have to know it's a capacitor. That if by some method of the transistor is not connected to a load, that is connected to no load and to, then it's just cut off. It remembers its state. Most recently turned on, it will remain on. And if that switch was most recently turned, is this, where this node really has a capacitance associated with it. And we call that a dynamic storage node. This is the switch model circuit diagram and the stick diagram for an inverter whose input has a switch connecting it, which can isolate that node and let it store charge. This is called dynamic because it won't remember forever. It'll remember long enough for most applications if you design right, but it will eventually forget. Question, Ted?
Is it dependent on that conversion from green to red, or will any transistor have this property?
Yeah, let me explain that. On the right there, you see a red line with a 0 on it as the switch that isolates the node. It requires a red-green crossing to do that, to turn it off. The other red-green crossing is the transistor that remembers. And so, in fact, between them, there must be a conversion from green to red. We use the black blob there to indicate that the two layers are somehow connected together, electrically connected. And the function of this, the output, is the complement of the stored value. That is, whatever the input was before you turned it off, the output remains the complement of that value. So this is an inverter with memory. Ed?
As a rule of thumb, in some random process that you can think of for sort of minimum size transistor and other garden variety values and everything, how much time could you expect to be able to store something?
How much time? This thing will remember typically many milliseconds. In fact, I guess you could say typically at room temperature, in good cases, possibly many seconds. However, a specification on a device, including temperature effects in worst case and everything, might be only 1 or 2 milliseconds. So there's a lot of variation depending on temperature and technology and so on. But it's easily long enough that if you're 100 clock cycles, you're okay. Okay, I'm going to go through some prepared notes here. As Doug mentioned before, there are two things we want to design. Those are registers, which will be made, as I just mentioned, with gates with storage nodes on their inputs, and combinatorial logic, the two types I just mentioned, switch logic or pass transistor logic, and the more conventional logic made out of gates, NAND gates, NOR gates, etc. An exception to these, the other kinds are large memories and analog circuits. These won't be discussed to any significant extent in this class, and therefore to do digital design, you only need to know for today at least. Talk about some of the complications, just introduce you to them a little bit later here. Okay, I'll define a gate as a load, a single load, plus some switch network connected to ground. By saying switch network, gates. But here's an for the switch, the NOR gate and the NAND gate you've seen. But it's entirely possible to build entire systems using only the inverter, using no NOR gates, no NAND gates, if you do logic with pass transistors. There's no logic that can't be done that way, and I'll show you that later. Trading the type of logic you choose to implement, gates versus switch logic, is a large part of this system implementation game, trying to decide which one is better for your application.
Is this considered switch logic right there?
This is not switch logic, this is gate logic.
That's okay.
Next. Okay, the switch model works almost completely, and you can assume that a logic 1 value turns a switch on. However, there's one exception to that, and that is the output of switch logic cannot be used to control more switch logic. For example, here's a switch. It's okay to control that switch by the output of this inverter. But it's not okay to control this switch by the output of that switch. So this brings up the need for using inverters at some points. And why is this? Well, as Doug mentioned, a switch is only on if its control voltage exceeds the source voltage by at least one threshold. So what will happen at this node is that when you turn the switch on with a 1 coming into it, its output will rise until it gets to one threshold below where the gate is, and that value will represent a logic 1. It won't go any higher than one threshold below the power supply, VDD minus V threshold. That's as high as it gets. If you then use that to control that switch, its output, by the same reasoning, will only rise to within 2 thresholds of the power supply, and therefore the value representing a logic 1 will be decreasing. To prevent this effect, you have to use what are called level restoring stages. Any gate logic, any inverter, NAND gate, or NOR gate has a level restoring effect. That is, its output for a logic 1 goes all the way up to the power supply, and for a logic 0 goes close to ground. That's very important. In fact, you can build the things this way and they will work, but they'll be very slow in many cases, and they won't work over a wide margin of parameters. I want to show you how you can make any arbitrary function with switch logic now. This is an example of using an 8-input multiplexer to implement any arbitrary function of 4 variables. Anyone who's taken a logic design class is probably familiar with this trick. That is, you build an 8-input multiplexer, in this case out of switch logic. A switch is represented here by this little red tab crossing the green wire. The inputs to this function are the logic variables A, B, C, and D, and we assume the existence of their complements also, A bar, B bar, C bar, and D bar. And these are run in on vertical metal wires, blue lines. Those can cross the green lines with no effect, recall. But wherever there's a little red tab hanging off of it, crossing the green line, it says there's continuity through that green line only if the corresponding blue line has a logic 1 on it. If you notice the position of those tabs, you'll find there's 8 horizontal green wires, each one of which corresponds to a unique combination of the input variables A, B, and C. So if we weight A with a 1 and B with a 2 and C with a 4, we can number the inputs 0 through 7 as I've done there. Now for each input, you can connect it either to D or its complement or to ground or to VDD. And the selection of these black blobs that make the connections defines the logic function that this implements. So notice there's no change in the size or the shape or the form of this function. It's a 4-input, 1-output logic function. That's got a certain nice regularity to it. Of course, there may well be a smaller and or faster way to make that function. But this illustrates the point that with multiplexers that can be built entirely of switch logic, you can build any function, any combinatorial logic function, easily and without having to worry about the topology and geometry of the thing too much. Okay, next. On a smaller scale, we find kinds of functions instead of 8-input. As you go to more transistors, lower, as you'll see, too many. Here's 2 different ways multiplexer. Algae. In that input and the output. Could be made smaller than blue lines, and because it hasn't got any of those black blobs in it which take up a lot of space, those contacts. Uses, remember Doug pointed out depletion logic 0 on its short circuit. It's turned on. So from every input to the output, there are 4 transistors in this case. And one of those paths will always have all 4 turned on if you're using this as a multiplexer that is driving the vertical lines by their 2 inputs and their complement. This trick with the yellow transistors has advantages, such as being small. It also has disadvantages, such as being slower because of more switches in series. So we'll see more about that problem later. There's other neat functions that can be built with this, but well, first let's look at the one use of this function block. One thing you can do with it, instead of hardwiring these inputs to some combination of VDD, ground, and the control signals, you can put some 4-bit number in there which then defines the function implemented by that function block. This is an interesting trick in that you can build this block which implements all 16 possible functions of 2 inputs, and you can dynamically change which function it implements. So this potentially is a useful trick for an arithmetic logic unit, say. And in fact, you'll see if you skim Chapter 5 in tonight's homework that the OM2 arithmetic logic unit uses 3 of these in each bit slice. And on the next slide, I think we'll see just a brief preview of a layout and what that looks like. In fact, we have the stick diagram and the layout of that function block. The green line going out the top there is the output. The red lines going horizontally are the 2 input values and their complements, and the 4 vertical blue lines are this 4-bit number n that tells it which of 16 possible functions to compute. And that lays out this way. This is a very compact layout. It's approximately the size of a gate. So in the area of, say, a NAND gate, you can implement a NAND gate and a NOR gate and an AND gate and an exclusive OR gate and change between them dynamically. So this is a very powerful concept. But as I mentioned, it has its speed penalties. Let's just take a quick look at how this is used in the arithmetic logic unit, 1-bit slice of the arithmetic logic unit of the OM2 computer. It's just to give you an idea of what a layout looks like. The interesting point here is that a layout is really just like a stick diagram. It's red and green and blue lines and black blobs. And the details of the dimensions you'll find out more about later. Okay, and there's 2 function blocks right in here. And they, in fact, share their red lines in this case. Here's a figure from the book which has a function block on the top. We've already seen that, so let's look at what's on the bottom of it. This is a tally circuit. Several of you may have encountered the problem of trying to design a circuit which will count how many of its inputs are true. There's various ways to do this, like a bunch of half-adders, for example. This is a circuit which has 3 inputs, x1, x2, and x3. And it counts by producing a true output on output z0, z1, z2, or z3 if that corresponding number of inputs is true. So if 2 inputs are true, no matter which 2 of these, then z2 will be a true output and the others will be false or 0. This is implemented by a fairly interesting technique, which is essentially to put in this logic 1 somewhere into this array, in this case the lower left corner. And then this array consists of green lines, which are a little bit hard to distinguish from the blue lines here, vertical ones. And the trick here is that each input takes that 1 as it comes in. That's like a token across if it has a 0, or it passes up to the next row if it has a 1. So the token gets by which output line it comes out to a 0. Zeros are switched in along all the edges of the array. So this is implementing a symmetric function. A symmetric function is a function that depends on what's are true particular set. Peter?
Dick, I'm having trouble with the colors on that diagram. You said that only the vertical lines are blue?
Yeah, the vertical lines are metal.
Okay, I don't understand the connectivity of the green lines. Do the diagonal lines connect to the horizontal ones, or don't
Yeah,
they?
now that's an interesting point. In stick diagrams, unlike the diagrams we're used to looking at, when wires cross each other, you'd think those aren't connected. But in stick diagrams, if they're the same color, they are connected to indicate that. Okay?
So the diagonal lines really aren't connected to the
They really are
horizontal ones.
connected. This is a connection. This is a connection, even though there's no black blob there. Since those lines are both green, they must in fact connect to each other. Okay. Black blob indicates a connection are different colors. So this is unlike the conventions you're used to in circuit diagrams. Okay. Ted?
I don't mean to be picky. You had the picture of what you're not allowed to do a while ago, which is connect the output of an inverter to the input of another stage. Is that
No, what you're not allowed to do is connect the output, such as Z0 there, to a gate that is the red line of a transistor.
Okay.
You notice here all the red lines are driven by the output of these, which is okay because of, you're not allowed to hook it to switch logic. You can hook it to any level restoring logic, but more logic. Okay? That's a good point to be picky on, by the way. Okay, let's go to the next one. Design, now that I've given you a brief introduction to combinatorial logic, is registers. Okay. Most of you are used to implementing digital positive edge triggered default. The property that the data in a flip-flop state where that's an use the two clock phases that Doug mentioned before. When phase 1 goes to the true level, whatever's on the D line gets connected to this storage node. The asterisk is there to indicate that that is, in fact, a dynamic storage node, and we are taking advantage of its storage capabilities. That's where the state of the flip-flop is stored. Okay, that signal gets inverted by this inverter, and when phase 2 is true, the inverse of what the input was gets stored on the dynamic storage node of the second inverter. And of course, it gets re-inverted so that the Q output is the same as what the D input was. But it's delayed, as this crude timing diagram shows. If you put a 1 in, which is stable during the time that phi 1 is true, then the next time phi 1 is true, that 1 is going to appear on the Q output and can be used as the input to another flip-flop. So by cascading these things, you can, of course, make shift registers. The delay from the data to the Q is 1 cycle, and in this case, it's non-inverting. The important thing about the MOS technology is that this basic 1-bit storage element consists of 2 identical parts. It's very symmetric. And if you split that down the middle, you have what's called a half register. A half register is an inverter with a switch on its input, nothing more. Okay? I'll show you how to make multi-bit registers, shift registers, and so on in a few minutes. Let me say a few more words about the 2-phase clocking methodology. First of all, the entire state of your nMOS design, if you follow this methodology, is stored dynamically. If you stop the clock, it's all over. The system forgets. Okay, this is not a technique for non-volatile and static type systems. There are no flip-flops in this system. This may come as a surprise to many people. And an even stronger statement follows. There are no loops at all in any combinatorial logic. This is one of the restrictions we put on our design methodology in order to simplify the analysis. It is not possible for there to be state stored in combinational logic networks if you follow this methodology. Of course, that precludes the use of flip-flops of any sorts. There's no cross-coupled circuits. Exceptions to these rules are quite common but seldom needed. That is, a lot of people don't follow this methodology, but I'm not aware of any good reasons for violating it with a few exceptions. The exceptions being things like, big RAMs and things that aren't very digital anyway. Okay, let's go on to the next one.
I have a meta question.
Yes. Most of these slides are direct. If you read Chapter 3, you'll see all this material. Although I did make some myself, and I can make copies of them if you're interested. It's what we call a dynamic register. Half register interchangeably. And when I say register, you should probably think a half register. That is, it's a set of inverters with gates on their inputs. This doesn't give you a full bit of delay. It gives you essentially one phase of delay. Two of these together makes a full register. A half register is often just as useful as a full register, though. You'll find ways to use them. To make an 8-bit register for your 8-bit microcomputer, you just put 8 inverters next to each other, put 8 transistors on their input wires, and hook them all to the same clock line. So what could be simpler? Of course, a more useful function is a register that doesn't load new data every time when you want it to. So you can do that by having a register which can take data either from the input or from nowhere at all. It'll continue to remember if you don't give it new data, but that only works for a while. So to make sure it will remember forever when you don't give it new data, you hook its output back to its input. You notice this is not a loop of combinatorial logic in the general sense, but that it's a clocked loop. It's isolated. And in fact, to really strictly fit the methodology, there would be a phase 2 clock in between here where it looks like it's slightly dotted. In this case, when phase 1 is on, there is a loop. So that's a sort of a mild violation of the no loops methodology.
It also means you can stop the clock.
If you only have storage elements, stop the clock with phase 1 high and load bar. Yeah.
Yeah, if you stop it with phase 1.
I don't know of any systems that count on that type of ability to stop the clock, but that's an interesting point. Okay. On the bottom, again, just like at the top, to make an 8-bit wide register, you just take 8 of those things and stack them up next to each other. When you design things like this, think of the cellular nature of things. When you design this figure 8, a selectively loadable dynamic register cell, keep in mind that you're going to want to stack up 8 or 16 of those most often, and that you should design them with control lines running in a direction that allows you to easily stack them, connect them together. So for example, the is a vertical line, probably red since it's going to the gates of all these things. Phase 1 and don't load is another line just like that. And those are driven from the edge somewhere. Okay, let's go on to the next one. I have another figure out of the book that tells how you hook these half registers together to make 1 bit of a shift register. This is the same figure I showed you in circuit diagram form when I started on registers. If you hook a bunch of those next to each other, what you have is an array of shift registers, or if you like, a 3-bit wide register or a 3-bit wide shift register, which can be expanded for more memory horizontally or for more bits wide in the width, in the vertical direction here. And there's an amazing variety of functions that can be implemented as nothing more than a bank of inverters with something slightly more interesting than a simple clock gate between them. And here's an example. On phase 1, all you do is you transfer the input in. But on phase 2, there's 2 things you might do. you can either transfer the input to the output or transfer it, shift it up one slot. So this is a shift up register array. And if you hook its output back to its input, then you can pass data in, store it, recirculate it as often as you like, and shift it up now and then. So you can also build it so it shifts the other way. So you might think of using something like this as a 1-bit upshifter in your ALU, and variations on it to make more powerful shifters and data extractors of various sorts. Okay. Let's get back to gates. I've talked now a few minutes about how you build functions with switch logic, pass transistor logic. I've talked about how you build registers using an inverter with a pass transistor on its input. The other type of device we make is sort of a cross between these. It's as in an inverter, it's got the load device. But as in a switch network, the device down here can be any arbitrary combination of switches to ground. But the important thing about a gate now is you have to start thinking about the switch model more carefully. In the pass transistor case, the resistance of the switches has no particular effect on the logical correctness of the function you've implemented. That is, no matter what the resistance is, you will eventually get enough charge through it to charge up the gate, that is the gate terminal of the transistor in the level restoring logic that it connects to, independent of the resistance, so you can make those transistors tiny. But in this case, the switch network, which in this case is what I call a driver device, not only has to remove charge from the output node to pull it to a logic 0, it also has to fight the load current that's always being provided by this load. So to do that, you have to look at what those resistor values actually are, pick some reasonable values to make it work. A simple way to look at this, okay, in the first place, let me go back and say most of what I've been saying is largely technology independent, whether it's CMOS, nMOS, or PMOS, or any kind of FET technology, gallium arsenide, what have you. There's always two kinds of devices. There's switches and there's loads. But now let's talk about the particular kind of load. In this case, it's a yellow transistor. It's an always-on transistor. And the nice thing about that is that the properties of these transistors are very similar to each other. The only difference is the threshold voltage. So when we talk about choosing reasonable values for their resistances, that will translate directly into reasonable values for their lengths and widths. That is very simple geometric parameters. If for a first cut at the analysis of what kinds of lengths and widths make sense on these devices, we assume we want a logic 0 on the output to be represented by a voltage that's, for example, less than 2/10 of the power supply. I picked that number because it makes the answer come out right. In fact, that's not a very good number. In the simplest case analysis, then, if the input is logic 1 and you want the output to be a logic 0 of 2/10 of the power supply, then this load resistance must be dropping 4 times as much voltage as this driver resistance. There are no other DC currents involved, so that resistance of the load must in fact be greater than or approximately equal to 4 times the resistance of the driver device. That factor 4 in there we'll call K, and that'll be a very important parameter that'll describe gates of all sorts. So keep that, that symbol K in mind, and keep in mind the value 4. I'll show you why. Now in red, a little note. In fact, as Doug mentioned, these things aren't really resistors, and the load device saturates. And as a result, the current you would get through that load is not as high as the current you would get if you modeled it as simply a resistor with a resistance 4 times the driver device. Since it provides on the order of half as much current as you would expect from that simple model, the output in fact falls to about 1/10 of the power supply, not 2/10. This is good, and in fact, this is not a very reasonable assumption to start with, 0.2 VDD. I just picked that because it came up with the right answer. And the right answer is that, in fact, the output low voltage is about 1/10 of the power supply. That is approximately a half a volt if you use a 5-volt supply. So it's approximately TTL compatible levels, which is only interesting when you go driving off chip. Okay.
Can you raise the slide a little bit?
Okay, so here's the point. Use the number 4 initially as the geometric impedance ratio. I use capital letter Z as an impedance. You can think of it as the sort of a non-dimensional impedance ratio of length to width. I'll show you some more about that later. The number 4 will be useful. Let's go to the next slide and see what a fragment of a layout looks like for that inverter circuit. The red and green crosshatched areas here are in direct correspondence to the lines on the circuit diagram, on the stick diagram. And where they intersect is the transistor. This lower transistor has what I call Z sub D. That's the geometric impedance ratio of the driver device of 1/2. You can think of that as an impedance. If this technology, this transistor has 1 ohm per square, which is not a reasonable value, then since it's twice as wide as it is long, it'll have a resistance of 1/2 ohm. In fact, you can multiply that by about 20,000 or so, and it makes sense. The upper device has a Z sub L, or geometric impedance ratio of the load device, of approximately 2. And the ratio, ZL over ZD, is this number we call K. That is, it's the ratio of the resistances of those simple transistor models. And in this example, I've drawn it with K equal to 4, as I showed you before. Notice the black lines on here. Typically in layouts and stick diagrams, black lines are used to indicate unspecified connections and various commentary type information. And notice on the output node, the line labeled out connects to the green region in the middle, also connects to the gate of the depletion mode load device. That's in order to ensure that the voltage from the gate to source is 0 volts. Also notice the sort of speckled region that I drew with a dotted line box around the upper load transistor. That's to indicate the implant, and would typically be shown on a color layout with a yellow block. I don't have yellow markers though. Okay, let's go to the next one. Have some examples of various kinds of gates now. Stick diagrams which are annotated with the ratios of the devices. This is one of the steps you have to take when you're actually designing a geometric layout. It's perfectly reasonable to think of this step being done for you automatically in some cases, but right now it isn't. Okay, on the top we have an inverter and a NOR gate. On the bottom is a NAND gate and an AND/OR invert gate. In all of these cases, I've used a impedance ratio of 1 on the load device, just for simplicity. The horizontal blue lines are ground on the bottom, power supply, or VDD, on the top. And in each case, I've labeled the geometric impedance ratio of the driver, or pull-down device. The interesting thing about this is that in the inverter and in the NOR gate, those devices are all 1 to 4. That is, they're 4 times as wide as they are long, which is a perfectly manageable ratio. Notice in the NAND gate, though, since there are 2 devices in series, their resistances effectively add. That's a first-order model of how a NAND gate works. I think you'd get a better explanation by looking at the detailed characteristics of those transistors. Read that in the book. But to first order, their resistances add, and therefore they have to be twice as wide to cut the resistance in half so that you maintain the overall 4-to-1 ratio. And the AND/OR invert gate, interestingly enough, is an easy thing to build in this technology. It requires only 1 load device. It has several parallel branches to ground. Those are the OR function, the OR invert part of the function. The AND part of the function is the series connection of transistors. Notice in this case, that on each leg you have to independently determine the ratios by how many transistors are in series. So on the leg with only 2 inputs, you see a 1 to 8 ratio, just as in the 2-input NAND gate. But on the leg with 3 inputs, you find you have transistors that are 12 times as wide as they are long. And if you stack too many inputs in a NAND gate or an AND/OR invert gate, you get this problem with the ratios start to get out of hand. And it's not just a problem that it consumes a lot of area, but it also is a problem because it takes a lot more charge to charge up that large gate on that device, and thereby slowing things down. Dan?
Is there a similar rule of thumb about how wide you can go in NOR gates?
Yeah, the rule of thumb on NOR gates is that you can go as wide as you like. There's essentially no penalty, except due to the stray capacitance of the interconnect.
So they turn off real well.
They turn on and off real well. NOR gates are real natural for this kind of a technology. For any kind of a technology where the switch devices have a non-negligible resistance. Okay, in relay logic, that wasn't true. NAND gates were just as easy to make because relay switches have very little resistance. Okay, any other questions? Yeah.
If you were building that AOI on the right, wouldn't you actually have a longer load rather than fatter input transmission?
Yeah, as I said, I drew the load devices with a ratio of 1 just for convenience. A typical ratio on a load will be twice or 4 times as long as it is wide, and that would take some factors out of these large widths. But for any given size load, you're going to get to the point where the width is going to get out of hand for large NAND gates. A typical way to design these things is with minimum size devices on the drivers, that is, square devices just as small as you can make them, and then make the load device long enough to work. That's a very low power way to design. It's also fairly slow, as we'll get into later. Okay. Now I have a simple rule to tell you about ratios. This is something you have to learn. It's another one of those rules like don't connect the output of a switch logic circuit to control more switch logic. This one says, even when you take the output of switch logic and connect it to restoring gate type logic, you have to do something different because, as I just showed you, k equals 4 is a good ratio. If the input signal comes from some other level restoring stage, another gate, that is someplace that has logic 1 equal to the power supply, or VDD. But if you're coming from switch logic, then logic 1 is represented by VDD minus V threshold. If that's the case, you need a larger ratio of impedances. And in this case, this is really a geometric ratio. It's not an impedance ratio. You need a larger geometric ratio because the driver transistor won't be turned on as hard, and therefore its impedance won't be as low as you would have hoped. So these are the two numbers that we tend to use a lot. It's, k equals 4 and k equals 8. And it's a very simple rule for which one to use. And here's an even simpler rule. K equals 8 works everywhere. You can design everything with geometric ratios of 8. But they may be quite a bit slower than what you can do by using k equals 4. K equals 4 gives you sort of a more or less optimum inverter and NOR gate and so on, because it's got a logic threshold in a reasonable place, and it's got reasonable drive capabilities.
Typically, the slowest edge is the rising edge, right?
Yeah, Ed says typically the slowest edge is the rising edge. And therefore, going to a longer, skinnier pull-up makes that even slower. That's why k equals 8 is slow. For more on how that factor is derived, you should read this one page, which is in tonight's reading assignment, page 21 in chapter 1. Will?
I'd like to request again a copy of the slides.
Copy of the slides, right.
At least those
All right.
that
I'll make
are
it.
not in the book.
I'll have them this afternoon if anyone wants to come by. Otherwise, tomorrow morning. Jeff?
Yeah, generally, Dick, I think we could pay a lot more attention to what you're saying if we didn't have to worry about getting down what's on the slides.
Yeah. It's yeah, it is in the book. You don't have to worry about losing it.
But reconstructing the sequence of the lecture is
Right.
a lot easier that way.
I'll hand them out. Okay. Ted?
As far as fast and slow, give me an example of fast and an example of slow.
Ted wants an example of fast and slow. Well, there was rumors of a circuit that had an input to output speed of anywhere from 80 nanoseconds to a half a second. But that's an extreme case.
That's slow.
I'll give you better examples later. In a few slides, we'll see how to estimate an actual gate delay in terms of real nanoseconds. In fact, that's the next slide. This will give you what you need to know to calculate that. The one number the most important number that the designer needs to be aware of in relation to the process that will be used to build his circuits is this number tau. That's the what I call the prime process parameter. It's called the transit time. An approximate definition, which I made up, I don't know if it's official, is that tau is the time required for a turned-on driver device, such as the one in the pull-down of this inverter, to sink enough charge to turn off another driver like itself. That is, for some given length and width of a device. Tau is the time that it has to be turned on before it's able to switch the inverter that comes after it. So if you put in a step voltage in the input of this inverter, that turns on its driver device right away. But the output doesn't fall right away. It falls as it discharges the capacitance associated with the next driver device, which is just like it in the following inverter. To really understand this, you need to know more about capacitance and resistance, and I wasn't going to talk about anything electrical in this talk. So let me just tell you that tau is about how long it takes for the output of this inverter to fall when you switch its input, assuming it's connected to another inverter like itself. And the output of the second inverter will start to move after its input gets down far enough. Its output will start to go up. And it'll go up considerably slower. Again, if it's connected to another inverter like itself, to standardize the amount of capacitive load on there, then it'll go up about k times slower. That's the same k that you saw in the geometric impedance ratio. And that's why k equals 8 is slower than k equals 4. So you see the rise time, as Ed mentioned, is slower by this factor k than the fall time. Are there any questions on that? Let's go to the next one. There's one other number that comes into calculating the delay of a device, and that's the fan-out. Here's an example of a circuit which has a fan-out of 3 at 2 nodes. By a fan-out of 3, I mean that the total capacitive load on that node is 3 times the capacitance of the driver device that's trying to pull it down. Okay, if F, the load on the node, that is transistor gate area relative to the driver device, K is the geometric impedance ratio of the gate that's driving that node, then we can say that the fall time of that node is approximately F times tau. That is just the fan-out times the transit time. Couldn't be a very simpler formula. So if you measure fan-out from your layout and you take transit time as given from the process, that's all you need to know to calculate the fall time of that node. And the rise time is simply k times slower. Now keep in mind here that these delay equations are not equations for the delay of a gate. At least I don't think of them that way. They're equations for the rise and fall time of a node. And that in fact, to calculate rise and fall time of this node, you have to look at the inputs of the gates that follow that node and the driving device or the output of the gate that precedes that node. Therefore, it's not a delay associated with one logic element, but it's associated with what's more the basic, prime element of a MOS design, which is a node or a wire. The delay through a pair of